Okay, so let's take a look at some more electromagnetics questions. So the first one here, we are asked, why must the output current in a step-up transformer be less than the input current? So if we think about this, we're told step-up transformer. So this means the voltage out has to be greater than the voltage in. For an ideal transformer, the power in is equal to the power out. So this implies that the current in multiplied by the voltage in is equal to the current out multiplied by the voltage out. Now, if V out is greater than V in, then this current out must be less than current in. Right, this is the only way to balance this equation. So, mathematically speaking, we need the current to be less than the input current. We need the output current to be lower in order for the output voltage to be higher. This is under the assumption that this is an ideal transformer where power in is equal to power out. So this is what we get. This is the general answer, and you can prove this mathematically. So we might do the general proof. So we can say that voltage in times current in is equal to voltage out times current out. This is a kind of proof. We want to rearrange this so it's in the form of current in. So divide both sides by voltage in. Divide both sides by voltage in. This tells us that the current in is equal to the current out times the voltage out over the voltage in. Now this is just some constant, and this constant is greater than 1. So this is some constant greater than 1. So this implies that we have the current in. It has to be greater than 1 because voltage out is greater than voltage in because it's a step-up transformer. This means that the current in is equal to K times the current out, where K is greater than 1. If you have K greater than 1, so let's say K is 2, that means the current in is 2 times the current out. That means the current in is double the current out, right? So this means that I1, the current in, must be greater than the current out. So this is how we can demonstrate this mathematically. We don't necessarily need to do the full proof to understand this, but it can be done. Now we have a second part to this question. So the second question here. Why is a laminated core transformer more efficient than a solid block? So this is really a definitional answer. We don't go into this in too much detail in the HSC curriculum. For those of you who go on to study electrical engineering, you'll do a lot more on specifically what types of electrical structures have what properties. So the answer that we, in a nutshell, pretty much is to do with eddy currents, right? So a solid block essentially is more affected by eddy currents. So if you slice the solid block into a series of metal plates and then you pretty much sort of glue them together as a big parallel plate transformer, there's just less space in which eddy currents can form, and so fewer eddy currents form, right? So solid block is more affected by eddy currents. Consequently, if you can avoid that design, you have fewer eddy currents. Eddy currents cause the inefficiency. Fewer eddy currents, you get less efficiency, right? But we should note that transformer design, the field of study that concerns how to actually make transformers, is very, very complicated, right? So if you actually talk to an electrical engineer who does design of components or things like this, there are any number of weird designs that are going to be efficient for various different reasons, right? So some types of transformers may be solid blocks due to size constraints, for example, right? It might be impossible to produce them at a small enough size to make it, or you might have some transformers which are just not stable enough unless they're not solid blocks, right? This is a whole field of research which is very, very complicated.